Swayam Prabha. Digital India. Educated India.
Welcome everyone to this NPTEL online certification course on techniques of materials characterization. We are in module 10, that is we are discussing about X-ray diffraction, and this is lecture 4. We are continuing with the discussion about intensity of diffracted beam, and until up to now we have seen in this module how X-ray absorption happens, what governs X-ray absorption, and then we discussed about X-ray filters as well. And we then discussed about the necessity of calculating this intensity of diffracted beam, because we have find out that Bragg's law, satisfying the Bragg's law is not the only condition. So, it is a necessary condition. Of course, if the Bragg's law is not satisfied, then definitely diffraction will not happen, but that does not guarantee we will get an intensity of this diffracted beam, because that somehow related to the position of atom or rather the atomic arrangement within any crystalline material. And from there we started our calculations. We understood that in order to calculate the final intensity of the diffracted beam, we should start from something like intensity from one single electron, and then we have to take it all the way to one single atom, and finally all the atoms which are containing within an unit cell. So, that is what we understood. And in the last class we started discussing about this, that when an X-ray beam interacts with an electron, what happens and what kind of an intensity we get out of it. So, we have seen that there are two different possibilities exist. One is the Thomson's effect, where it is kind of an elastic interaction, and here this incoming X-ray wave is basically cause this electrons charge particles to oscillate, and in that process continuous acceleration deacceleration process, it generates another kind of X-ray which is having almost the same same frequency and wavelength as the incident X-ray. So, it is a kind of coherent radiation is produced in the form of an X-ray. So, that is a one kind of an scattering of X-ray. And we have also seen another effect, that is a Crompton effect, where we saw that it is when an X-ray beam hits the electrons, then it will some amount of energy is transferred as a kinetic energy to this electrons, which is called Crompton recoil electrons, and some part of the energy will be then lost, and that scattered beam it will be deviated from its original path, and that scattered beam will have a lower energy and correspondingly higher wavelength from this from the incident X-ray. So, these two types of phenomena are possible whenever an X-ray beam is interacting with the electrons. So, with that we will be now discussing about the scattering of an atom, and then we will discuss about the atomic scattering factor, what is the importance of this in calculating the intensity, final intensity of diffracted beam. We will try to see a little bit relationship between diffraction and scattering, and if time permits we will also try to start our discussion about scattering by an unit cell, which we will continue in the next class as well. Okay, so let us start with this scattering by one single atom. So, what we just discussed, what we understood, that whenever an incident X-ray falls on a material, and that material contains various type of atoms, lots of different electrons, it has a positively charged nucleus in the middle, and the electrons, there are not one single electron, but there are lots of electrons, various electrons are there, and this electrons, of course, each of these electrons will be interacting with this incident X-ray by either Thomson scattering or by Crompton scattering. Okay, so this two phenomena is possible, and Thomson scattering we already understood that Thomson scattering is governed by this Thomson's equation, and here in this equation we can find out the intensity of the scattered X-ray beam in terms of the intensity of the incident X-ray beam plus some other factors like the scattering angle as well as the dielectric constant of the medium, and then mass of this charged particle and the charge of this charged particle, all of these things. And we also discussed in the last class, if you remember, that for diffraction purpose, only the Thomson scattering is important to consider, not the Crompton scattering, because Crompton scattering it's kind of a random process, and in that random process the change in wavelength of the scattered beam is not a fixed. It doesn't have a definite relationship with the incident X-ray beam. So that is why this Crompton scattered X-rays will have a range of wavelength, and that's why this cannot be considered for a diffraction purpose, because diffraction is very much, you need a constructive interference. After the X-ray beams are generated from various electrons, various atoms and all, you need to have a constructive interference. That means the waves which are generated out of this interaction, the waves should have a phase relationship between themselves, or should have a definite relationship with the incident beam, and in the process they will have a definite relationship between themselves as well. So this doesn't happen for a Crompton scattering, and that is why we cannot consider the Crompton scattered or Crompton modified X-ray radiation for diffraction purpose. So diffraction for now onwards, in the diffraction purpose, in this entire discussion from here onwards, like when we calculate the scattering of an atom and then we take it all the way to an unit cell, all we will be considering is basically Thomson scattering, no Crompton scattering, but definitely we will come back to Crompton scattering, because I told the Crompton scattering is important because it is basically forming the background of in the X-ray diffraction profile. Finally what you get, it causes the background. So that is also important to consider. We will come to that. Anyway, so one question at this point comes, and many a times my students ask me, and that may arise to you as well, that why we are considering only the electrons in this process. An atom consists of nucleus as well, which is again a charged particle. So the way electrons acts as a source of another electromagnetic wave generation, the nucleus can do the same thing. They are also positively charged, and if they are set in an oscillatory motion, they can also produce another set of electromagnetic wave. True. Point is, the nucleus is heavily charged, and also its mass is much higher than the electrons. So that is why the incident X-ray photon, it is not possible for them, they are not energetic enough to cause or to put the positive for most of the materials, except for very small, very light elements, I would say. Except for them, for most of the general type of materials that we put for X-ray diffraction, for them the positively charged nucleus is heavy enough, and that is why they cannot be put into oscillatory motion so easily by the incident X-ray. So we can safely neglect the interaction between a nucleus and the incident X-ray, and then the resulting effect on the diffraction. So we can safely neglect this, and that we can also check from this equation, Thomson's equation, because here if you look at here, this intensity of this electromagnetic wave or the X-ray that is scattered, that intensity of that X-ray beam is inversely related to the mass of this particle, charged particle, which is acting as a source of this electromagnetic wave. So nucleus is heavy, and that is why the wave, even if we consider that it generates some wave, the intensity of the wave will be very small. So we can safely neglect that. So that is why the nucleus doesn't come into play, and all we will be considering here, Thomson scattering, coherent Thomson scattering from an atom, is only due to the electrons content in the atom. So we just need to consider the Thomson scattering from electrons in order to calculate the final scattered intensity from one complete atom. Okay, that is first condition. Now the question comes, already we said that there are many electrons here within the atom, within one single atom. Here there are, you can see there are 3 electrons I have seen, but we know that many electrons are there, and the number of electrons is of course related to the atomic number Z. Fine. So now if we want to calculate the total intensity of this entire atom, the question is, should we that intensity, that wave that is coming out of the incident X-ray interacting with all the electrons, and finally the wave, the scattered wave that is coming out of this atom itself, that intensity of that wave, is it simply the sum of the waves scattered by all the electrons that it contains? Okay? Or we can put it in another way, if an atom contains its atomic number is Z, and that means the atom contains Z number of electrons, then the scattered wave from this entire atom is the amplitude of the scattered wave, is it simply Z times the amplitude of the wave scattered by a single electron. Okay? And that means we have already seen that this is the intensity from a single electron at a measured at a point P, which is at a distance of r. So, this is the intensity of that Thomson scattering, and expressed in terms of again the angle that this scattered beam and the incident beam is making, and of course, with the respect to distance. So, is it simply the Z time or Z time multiplied by this IP? Is that the total intensity of the scattered X-ray beam coming out of an atom? Okay? That is the question. Point is, if you put a photographic plane here, okay, what you will see is that depending on the direction, right. So, if you put a two-dimensional photographic film here, and you will see that only in the forward direction the intensity is highest, and then in any other direction the intensity goes down. So, that means this intensity that we have collected here definitely has a relationship with the angle that the scattered beam makes with the incident X-ray, which is, this relationship is anywhere there. Definitely, this also says the same thing, that the intensity will be highest if we are checking only in the forward direction. Okay? This we have discussed, that IP, the intensity coming out of Thomson's intensity coming out of an electron, that will be the highest, that intensity will be highest if we are in the forward direction. In any other direction, this entire term will be less than unity, and correspondingly IP will also be lesser than the forward direction or extreme backward direction. These two are the directions where the intensity will be highest, correct. Point is, this is valid, that we can simply calculate the intensity of the X-ray beam coming out of the atom is Z times IP. This is only valid in the forward direction, okay, where all the atoms or all the waves coming out of the Thomson's waves, scattered waves coming out of each of these electrons, all of them will be in phase. So, when we sum up these waves coming out from the electrons, we cannot simply add up their amplitude, because this is a wave and they have a phase as well. So, we have to take care of that phase relationship between various electrons. So, only in the forward direction, simply we can call that it is an amplitude. We can just sum up their amplitudes, and we can, just because here in the only in the forward direction, all of them will be having the same phase, right, all of these electrons. So, waves coming out of this electron, wave coming out of this electron, wave coming out of this electron, all of them will have intensity simply in the expressed in terms of their amplitude. Phase will not be important there, they will that phase relationship, this will come, this term will come as 1, simply unity. So, because all of these beams in the forward direction, they are all in phase, we can simply, only in the forward direction, we can simply add their amplitude, and that will be giving finally their intensity only in the forward direction. What happens for other direction? That is what we have to define, or we have to derive, or rather what happens in any arbitrary direction other than this forward direction. In any arbitrary direction, if we want to calculate, or if you want to know the intensity of the diffracted beam, what will be the relationship? That is the point here. Now, of course, electrons of an atom are situated at different points in space, here like this, fine. So, we are considering this atom, and this atom has this nucleus, and it also has this electrons, many number of electrons in different places. We just put for a schematic purpose, just to understand this, we have put them in different places. Okay, fine. Now, we imagine, and all of these electrons, just now we understood that all of these electrons will have difference in phases. Only in the forward direction, all of them will have the same phase. Any other direction, they will have a phase relationship, and this we can check it also. Let us imagine that we are considering two electrons, one is A and one is B here, okay. And if we check the intensity, so this A is producing one wave, so X-ray beam, this incident X-ray beam is causing one type of wave, scattered wave, and this B, when it interacts with B, it generates another X-ray beam, another scattered beam. So, if we consider in the forward direction, if we measure the intensity here, that means if we just sum up these two waves, basically they will be on the same phase because they travel, these waves now travel the same distance before and after the scattering. So, if we check this, if we take it from the source, let us imagine that this is a source. So, these waves basically have traveled the same distance, the entire distance, whether before and after. So, this wave in here, it has traveled less before scattering and more after scattering. This one here, more before scattering, less after scattering, but overall the entire distance is the same in the forward direction. So, that is why they are in phase. We know that phase related to the path difference basically. So, here there is no path difference and the phase is same. We will be getting intensity, if we add them up, they will simply be added because their amplitudes will be simply added, that is it. Okay. Now, if we imagine other than this forward direction, if we imagine some other scattered beam in the same direction, let us imagine. So, let us think that from electron A, I am getting another scattered electron beam instead of forward scattering. I am getting a scattered beam which is going in this direction and making an angle 2 theta, okay, with the incident beam here. This angle, let us imagine that this is 2 theta, and from atom B also there is another scattered beam that is generated and making the same angle 2 theta. So, finally, we are trying to calculate the intensity of this scattered beam from this entire atom in this plane, in this direction y dashed, meaning on this plane, on this direction, I am trying to add up these two waves here and trying to find. This is completely arbitrary because 2 theta can be any value. So, I have to find out an expression on this for this arbitrary direction, any arbitrary direction. And as we already understood, immediately understand that this path difference is now not the same for atom which is, or for the wave which is scattered from A, point electron A, and the atoms which is scattered from point or electron B. This two has completely different path, they have traveled different distance before and after the scattering. That is why they will be having a path difference between them, which will translate into their phase difference, and we will have something like a partial interference. It will not have a complete interference or complete constructive interference. If you put it in this way, they will have a partial interference there, and that will modify the resultant wave that we will be getting somewhere over here will have its amplitude, its intensity modified. That will not be a direct summation of these two. So, the net amplitude in this direction will be less than that of the wave scattered by the same electrons in the forward direction. So, here if we calculate the intensity in any other direction other than forward direction, it will have a comparatively lesser intensity, and that is what we have shown here, that only in the forward direction, and that is now this is not only because of this is because of now electrons or waves coming out from two different electrons altogether. So, in the forward direction only we will get maximum intensity, and the more we are going further away from this forward direction, meaning the 2 theta, as the 2 theta is increasing, we will be getting a lesser and lesser intensity, okay, from, and that is how the entire relationship of this diffracted beam intensity or X-ray, we are now not in diffraction, we can call that this is a scattering. So, the scattered beam, intensity of the scattered beam from one single atom, this is how it is related to the intensity of scattered beams from different electrons that it contains. So, this is how it varies depending on which direction I am looking at, or what is the relationship, path difference, phase relationship between the scattered beams from various electrons. Okay. So, the best way we can understand this summation, or best way we can calculate the intensity of the scattered beam coming out of one single atom here, let us say any arbitrary direction, the best way to express is this one is by a term called atomic scattering factor. Okay. So, atomic scattering factor is simply expressed the efficiency of scattering of a given atom at a given direction. So, in any given direction, anywhere here other than even including the forward direction, any direction, what is the efficiency or what is the scattered beam intensity, how the scattered beam intensity is related to the scattered beam intensity from single electrons, individual electrons, the the intensity of the scattered beam from the overall atom, how it is related to the intensity of the scattered beam from individual electrons that it consists. That is along any given direction. Okay. So, that is expressed by this atomic scattering factor. And the way we can put this atomic scattering factor, it is simply a ratio of amplitude of the wave scattered by an atom with Z electrons, that means the atomic number is Z, and divided by the amplitude of the wave scattered by one single electron. Okay. So, one single electron, whatever the amplitude of the wave, and that is it divides to the amplitude of the wave scattered by the entire atom. That's the atomic scattering factor. So, of course, in this relationship we are taking the direction as well. How? Now, the point is how we are taking the direction. It is simply taking the ratio of this amplitude. So, how the direction thing comes out here. Basically, if you now consider, as we already said, that if you are considering the forward direction, only the forward scattering direction, there this amplitude, and we said that simply you have to multiply, right. You have to just sum up all the waves, their amplitude summed up, because they have no phase difference amongst them. So, there what will happen, the atomic scattering factor will be simply atomic number, okay, F equals Z for any along the forward direction, for any atom scattering along the forward direction. So, if we consider the intensity, if we measure the intensity here, so this intensity will simply be the amplitude of it will be simply the atomic number of it. So, that means if we measure it here, so in the forward direction, exactly in the forward direction, this intensity will be some multiplied, it will be related to the, it will be proportional to the atomic number of that element, okay. Simply atomic number, nothing else will come, no phase, nothing, no other expression will come. Now, as the theta increases, already we saw that as theta increases here, the angle 2 theta, basically this 2 theta, the angle that scattered beam makes with the incident beam, as this angle increases, then the wave scattered by individual electrons will be more and more out of phase, okay. So, if you increase this scattered, this angle, if this angle increases, electrons will be going more and more out of phase. So, if this angle increases, if we consider another ray which is something of like this direction, which is possibly, if I can draw this here, if I consider, okay, let me change it to a pen, okay. So, if we consider, let us say another direction here, something like this direction, where I have this angle to be some other 2 theta 1, then what we can get is that basically what we are getting here is this, if this 2 theta is increasing, so this direction if we are taking and then some other direction, so here the 2 theta is increasing, and then we will be having F more this beams here, if we measure it here somewhere over here, they will be more and more out of phase compared to something like here. So, that means the atomic scattering factor will decrease as the theta will increase from the forward direction. As the theta will increase, the atomic scattering factor will also be increasing. The atomic scattering factor will basically decreases from the F equals Z, that is the forward direction. So, if we are moving to any other direction from the forward direction, continuously the atomic scattering factor F will decrease from a value F equals Z. Okay, simply like this. So, atomic scattering factor, the first thing it depends on is basically the angle that the incident ray makes with the scattered beam makes with the incident beam, and that is precisely because you can prove this geometrically as well. Why this will go more and more out of phase, because as it is moving in this direction, and this path difference will be like will be sort of the lambda, the wavelength of this lambda will be, path difference will be larger relative to the wavelength. So, that's the only point which will happen, and therefore, the theta will be reducing. So, this we can also see from other perspective as well. So, the atomic scattering factor will also depend on the wavelength of the X-ray beam. So, number one, it will depend on the angle 2 theta that this incident beam and scattered beam is making with the incident beam. That is the first thing atomic scattering factor depends on. The second thing it depends on is the wavelength of the incident beam. So, if for a fixed value of theta, if we imagine that we are still considering this direction, if the wavelength decreases, okay. So, if the wavelength decreases, then what will happen? This path difference will be larger compared to the wavelength. So, wavelength is much lesser here, theta remains the same. So, we are taking still again we are calculating, we are summing these two waves in this direction, theta remains the same. If the wavelength is reducing, then the path difference will be larger compared to the wavelength itself, and that means the these two waves which is generated from these 2 points will be now more and more out of phase from there. So, path difference depends on the wavelength, that also we have seen. When please recall, if you are not able to understand here, please recall the way we have geometrically we derive the Bragg's law. The similar type of derivations now we can do, and we can find out that the path difference, if the lambda decreases, we will have path difference more and more out of phase. So, that the path difference will not be an integral multiple. The chances of path difference to be an integral multiple of lambda will be lesser if the lambda goes down, and same thing, the path difference will be an integral multiple of lambda. This possibility will go down if we increase the theta, and this geometrically can be proved. I am not going here. If you like, you can try this. Okay. But what we are saying here is now is that for both this atomic scattering factor will depend on the theta as well as on lambda, and actually this atomic scattering factor will involve not theta, actually it depends on sin theta. So, ultimately the atomic scattering factor will decrease as sin theta by lambda. So, it is inversely proportional to the lambda and it is directly proportional to the sin theta. As the lambda decreases, f increases. Okay. I mean the shorter the wavelength, the greater interference. So, this lambda f will be smaller. So, f will decrease as lambda is becoming smaller and smaller, and it will also depend on the sin theta. As sin theta decreases, as sin theta increases, lambda f will also decrease. So, basically ultimately f will decrease as the quantity sin theta by lambda increases, this one. So, this is the final relationship that we can get about atomic scattering factor. F is inversely related to lambda and f is directly related to sin theta. Okay. So, this is finally this is the relationship. Sorry, I said in the other way around. Basically, f is directly f is inversely related to sin theta and directly related to the lambda. If lambda decreases, f will decrease. If sin theta increases, f will decrease. So, ultimately this entire term sin theta by lambda, if this term increases, then overall f will decrease. Okay. And remember one thing, if this sin theta and lambda cannot be varied independently, sin theta and lambda varies together from the Bragg's law. So, if you vary the lambda, sin theta will automatically vary. If you vary the sin theta, lambda will automatically vary. So, that's why this entire term sin theta by lambda is considered as one single entity, and what we plot here is basically the variation in atomic scattering factor with respect to the term sin theta by lambda, which is expressed normally in angstrom inverse. So, distance inverse unit. So, what we now see is that the atomic scattering factor here. So, and atomic scattering factor, one important term is atomic scattering factor is also called the form factor sometimes, because it depends the way in which the electrons are distributed around the nucleus. So, atomic scattering factor also depends that where exactly these electrons are. So, from which electrons. So, the position of the electrons is also important in determining the f value, amplitude value, but we are not considering it here, we are not going into that. Anyway. So, now if we see this variation of atomic scattering factor with respect to the sin theta by lambda, this term. So, obviously in the forward direction when they are at the 0. So, 0 means sin theta equals basically 0. So, that is the forward direction. So, in the forward direction here the atomic scattering factor is equals to Z, and this is we are seeing it for copper is Z equals 29, that is for copper. So, at the forward direction when sin theta equals 0, we are seeing that the atomic scattering factor is equal to the atomic number, and then as this term increases sin theta by lambda, as we are going away, both sin theta is increasing, lambda is decreasing. So, as we are going away from the forward direction, as well as the intensity, as well as the wavelength of the incident X-ray is decreasing, the atomic scattering factor is continuously decreases, and finally it decreases to a very low value in the backward direction, that is when 2 theta equals 180 degree, that means theta equals 90 degree. In that case, when 2 theta is equals 180 degree, again this is sin theta equals this lambda value. Now the theta equals 90 degree, so sin theta is 1. There itself, there also this value is very less, or otherwise very short wavelength, that will also make this atomic scattering factor to be of very small value. So this atomic scattering factor, the importance of this graph is, this is basically telling you, if you just consider one single atom, how the intensity of that one single, the X-ray beam scattered from one single atom, how it is varying with the angle that this scattered beam is making with the incident beam and the X-ray intensity, how the intensity of the scattered X-ray beam is varying in case of a single atom. So that is what is shown by this graph here. Okay, that is the importance of this graph. So from here we will stop here and we will continue with few of the other issues in the next class. Thank you.